Okay. Okay. Sorry, no sound this time. Sorry about that. Okay.
That's better.
Okay.
Yeah, no,
All right.
nothing
Yeah,
like
holy shit.
I don't know what happened. Sorry. Okay. So let me share my iPad again. Okay. Can you see my screen? All right.
yeah,
Okay.
yes.
Okay. Let's continue. To check if A and B are independent, we calculate PA given B. Again, given means the condition. Okay. And PA, this is PA given not B, which means B not happens. Okay. So not B means the head is not on the first choice, which means we have tail on the first choice, which is these two cases. Okay, not B. So PA given not B again will be 1 over 4 divided by 1 over 4 plus 1 over 4. So still 50%. So PA does not change whether B occurs or not. So then we say A and B are independent. Okay, so you get the idea of what is independence. Okay. All right. So another candy problem. Okay. The bowl has five candies, two red, three blue. Choose two candy randomly and define A. The second candy is red, and B, the first candy is blue. All right. Okay, so let's first calculate what is PA given B. All right. So first, let's figure out what is condition. So B given B means given the first candy is blue. So after the first pick, the first candy is blue. Then the second pick we have two red and two blue. Okay. Then what is probability that the second pick is red, given the first pick is blue? So we have two red and two blue, and the chance we get red will be 2 over 4, right? So we have two red and two blue. So that's 2 over 4, that's 50%. Then let's look at what is PA given not B. Means given the B not happens. Okay, so given the B not happens means the first candy is red, right? So B is the first candy is blue. So not B means the first candy is red. So if the first candy is red, then we have one red and three blue remaining. So the chance for the second candy is red will be 1 over 4 total. So it becomes 25%. So given B occurs or not, PA does change. Then we say A and B are dependent. Okay. So multiplication rules. If A and B are two events and PB not equal to 0, right, then PA is and and B is equal to PA given B. That line means, again, given times PB. Okay, so this is, equal to what we just know for the conditional probability. PA given B is equal to PA and B over PB. Okay, so you move this part to the left side, you get this equation. Okay. And the same thing for this equation. PA and B is equal to PB given A times PA. Okay. And if PA and PB not equal to 0, then both of the two equations will be true. And if these two events are independent to each other, okay, then the equation will become this one. If they are independent, PA and B will be PA times PB. Okay, for example, we toss a coin twice. Okay, so the probability, let's say the first pick is head and the second pick is head, second toss is head, will be equal to the probability of the first toss is head times the probability the second toss is head. Okay, because these two toys are independent, so that will be 50% times 50%. Okay. If we have more than two independent events, all right, okay, again, the character kind of messed up. If A1, A2, AN are independent result, then this event should be PA1, times and A2 and A3 and AN will be equal to PA1 times PA2 times PAN. Okay. If these events are independent. Right, so another example. We have a microprocessor manufactured by a certain process. 20% are defective, and we have 5 microprocessors chosen at random and tells us the function independently. Okay, these 5 processors are independently microprocessor. Okay, asking what is the probability that they all work. Okay, so the probability they all work will be equal to the probability the first work, W is for work, okay, and the second also work, and the third work, and fourth and fifth all work. Okay. And because they function independently, we simply use P, the first work, times second work, times the fifth work. Okay, will be 0.8 to the power of 5. Okay. Because they function independently. If the question asks, what is the probability that at least one work? Okay. Here we're gonna use a trick which we'll use quite a lot. in the future. Okay, so we can think what are the possible outcomes. We have 5 microprocessors. Okay, so we could have 0 works, okay? Or we could have only 1 work, or we could have 2 work, or 3 works, or 4 work, or all 5 works. Okay, so these are the possible outcomes. So the question asks, what is the probability at least 1 work? So by intuition, you probably think, we should use the probability has 1 work, okay, and plus the probability like 2 works plus 3 works plus 4 work plus all 5 works. Okay? Or you can use a much simpler way. They say at least 1 work. Okay. It is also equal to, so P at least 1 work. That is equal to 1 minus the probability none of the 5 microprocessor work. So this is a much simpler way to calculate. Okay, you think of what are all possible outcomes. So the probability at least 1 work plus the probability none work will equal to the whole sample space. So 100%. Okay. The probability none work will be pretty simple, okay, because they are independent. So probability none work will be probability first not work times second not work times fifth not work. Okay, so that will be 1 minus. So the probability of first one not work will be 20%. So 0.2 times to the power of 5. Okay. So we just ask, how we can determine the events are independent or not. Okay. The best way, as we can see here, is we think thoroughly the process that produced the event. Okay. For example, if a coin is flipped twice, then obviously the outcome of the second flip will be unaffected by the outcome of the first, not second. Okay. It is also reasonable to expect the outcome of people attending the sport event depending on the ranking of the visiting team. So think about all the possible ways if 2 events are independent to each other. Okay. The item in a random sample may be treated as independent unless the population is finite and the sample size is large enough. Okay, the sample size is more than 5% of the population. So, remember one of the previous example? So, in a sample space, we have 2 A's and 2 B's. Okay, then the second peak will be depending on the first peak. So if the first peak is A, then the second peak we get A will be 1/3. Right? We have 1A and 2B. If the first peak is B, then the second peak we get B will be 1A will be 2/3. Okay. So the first peak and the second peak will be dependent to each other. That is because the sample size is much larger than the whole population. Okay. Then we have another example, right? So we have 2 million A's and 2 million B's. Okay. Then the first peak and second peak will be virtually independent of each other because the population size is 4 million. It's too big. So no matter whether the first peak is A or B, the second peak is still 50%, okay, in practice. Okay, so that is where this tells us. When the sample size is larger than 5% of the population, then we may think the peaks are dependent to each other. Okay. All right. The law of total probability is another new concept. I don't think we can finish the discussion here for today. So let's save it for Tuesday next week. Okay. So yeah, let's stop here for today. I know we introduced a lot of new idea, permutation, combination, under what condition we use which equation, and also conditional probability. What is A given B means? Okay, so we have a lot of to digest for today. Make sure to review lecture notes and also the textbook if possible. I'm gonna see you Tuesday next week. Okay. Questions?
Professor, I have a